Alright, let's talk about hash tables and the double hashing open addressing collision resolution technique. So just a quick recap for those of you who don't know how we do insertions into hash tables for open addressing. We start with a variable x initialized to 1. We compute the hash value of the key. We set that to be the first index that we're going to check in our hash table to see if it's not null. So the goal is to find an empty slot. So we're going to loop while we are still hitting spots where there are already keys. And every time that happens, we're going to offset our key hash using a probing function. In our case, it's going to be the double hashing probing function. And we're also going to increment our value of x so that we keep probing along further and further. Once we find a free slot, then we can insert our key value pair into the hash table. Okay, so what's the deal with double hashing? So double hashing is just a probing method like any other, but what's special about it is that we probe according to a constant multiple of another hash function. So specifically, our probing function looks something like this. We give it as input the key, which is a constant, and the variable x, and then we compute x times h sub 2 of k, where h2 of k is a secondary hash function. So here's an important note. h2 of k must hash the same type of keys as h1 of k. So if your key is a string, well, h2 of k must hash strings. If h1 of k hashes integers, then h2 of k must also hash integers. So here's a note I put at the bottom that notice that double hashing actually reduces to linear probing, except that the constant is unknown until runtime because we dynamically compute it with h2 of k. So since double hashing reduces to linear probing at runtime, we may be stuck with the same issue we saw with linear probing, which is that we get stuck in an infinite cycle. So if p of x equals 3x, meaning our secondary hash function at runtime calculated a value of 3 for the constant, and say h1 of k was 4, and the table size was 9, then we might end up with the following cycle occurring. So the cycle produces values of 4, 7, and 1, which makes it impossible to reach any of the buckets 0, 2, 3, 5, 6, and 8. So if 4, 7, and 1 are already occupied, that means we're stuck in an infinite loop inside our hash table and we're not able to insert our key value pair because we're not able to go anywhere else. So this is an issue we have to deal with. So to fix the issue of cycles with double hashing, here's one strategy. We're going to pick our table size to be a prime number, and we're going to compute a value called delta. So delta is just going to be h2 of k mod n, but occasionally delta might be 0. And if that's the case, then we're going to be guaranteed to be stuck in a cycle because we're not going to go anywhere when we probe because we're going to be multiplying by 0. So when this happens, just set delta to be equal to 1. Alright. So here's a justification why this works. So notice that delta is always going to be between 1 inclusive and n non-inclusive. So the greatest common denominator between delta and n is going to be 1, since n is a prime number. So therefore, with these conditions, we know that the probing sequence is guaranteed to have order n. So we're going to be able to hit every single slot in our hash table. So given that there's at least one free slot in the hash table, which there will be because we're keeping our load factor below a certain threshold, then we're going to be able to reach that slot. Okay, so here's a core question. How do we construct our secondary hash function? Suppose the keys we're using have type T. And whenever we use double hashing, and we need to construct h2 of k to hash keys that are also of type T. So it would be really nice if we had a systematic way of generating these new hash functions every time we need one, right? Because we might be dealing with multiple different data types of type T. So luckily for us in computer science, almost every object we ever create is constructed of the same fundamental building blocks, in particular integers, strings, real numbers, fixed length vectors, and so on. So we can use this to our advantage. Luckily, there are many well-known hash functions for these fundamental data types, and we can combine them when we want to construct our new hash function, h2 of k. Frequently when we compose hash functions, we select them from a pool of hash functions called universal hash functions, which generally operate on these fundamental data types, which is quite convenient. Alright, let's have a look at an example with double hashing. So suppose we have an originally empty hash table above, and we selected our probing function to be p of x equals x squared plus h sub 2 of k, which is what we need it to be, and our table size to be n equals 7. Notice that that's a prime number, and we set our max load factor to be alpha equals 0.75, so our threshold to resize is 5, so once we hit 5 elements, we need to grow the table size. Alright, so let's insert all of these key value pairs on the left into this hash table. So first key value pair is k1 and v1. Now suppose that the hash value for the first hash function of k1 is 67 and h2 of k1 is 34. Then first thing we do is we compute delta. So we compute h2 of k1 modulo 7, which is the table size, and we obtain 6. And then we compute where this key value pair should go, and it should go at position 4. So now k2, suppose h1 of k2 is 2 and h2 of k2 is negative 79. So delta is 5, but we're just going to insert at position 2 because there's no collisions. So h1 of k3 is 2 and h2 of k3 is 10. These are just arbitrary numbers I chose for these hash functions. So then delta would be 3 in this case because 10 mod 7 is 3. So we have a hash collision because we're trying to insert our k3 at index 2, but k2 is already there. So what we need to do is we need to probe. So we're going to compute the position to be our original hash function position, so h1 of k3 at position 2 plus 1 times our delta value mod 7, that gives us 5. So we're going to hop to position 5 right there. Alright, now let's insert k4. So suppose now that h1 of k4 is equal to 2 and h2 of k4 is equal to 7. So let's compute delta. So h2 of k4 modulo 7 is equal to 0 because 7 mod 7 is 0. So when this happens, we know that we need to set delta equal to 1 so that we don't get stuck in an infinite loop. So now h1 of k4 plus 0 times delta mod 7, that gives us 2. So we have a hash collision at the bucket for index 2. So we need to keep probing. So now we probe by multiplying by delta. That gives us index 3. And then we were able to insert. So now we're going to try insert k3, which is already in our hash table actually, but with a new value. So we're going to be performing an update this time. So suppose h1 of k3 is equal to 2. Actually, we should have known that from before. and h2 of k3 is 10. So we compute delta. So we have a collision. And we find k3, which was already in there, and update its value. Now suppose the first hash function for k6 is 3, and the secondary hash function of k6 is 23, then that gives us a delta value of 2. So when we try to insert it, it goes to position 3, so we need to probe. So we compute 1 times delta mod 7, that gives us 5. There's another collision, so then we compute the offset at 2 times delta mod 7, which gives us 0. And we find a free slot, so we're able to insert our key value pair there. So notice that we actually inserted 5 elements, so it's time to resize and grow the table because we've reached the maximum threshold. So one strategy when we're trying to resize the table with double hashing, because we need to keep our table size to be a prime number, is to double the table size and then find the next prime number above this value. So in our case, when we double, we get 14, and the next prime number above 14 is 17. So 17 is going to be the new table size. So allocate a new table of size 17 and go through the elements in the old table and insert them into the new table. So from before, h1 of k6 is 3 and h2 of k6 is 23. So we compute delta, and we know we're going to put it at position 3 and there's no hash collision. Next up, nothing in position 1. In position 2 we have k2, so the hash value for k2 is 2 and the secondary hash value for k2 is negative 79 from before. So compute delta to be 6. So we're going to insert that at position 2 with no collision. Next one, k4. So we know h1 of k4 is 2, and h2 of k4 would be 7. So we compute our delta value, and notice that our delta value now is not 0, which it was before, but 7 because our mod is 17. So delta is 7. So we have a hash collision here, but we need to keep probing. So compute the offset at 1 times delta, which gives us 9 mod 17. Next one, insert k1. Suppose h1 of k1 is 2 and h2 of k1 is 34. Then compute delta, and that gives us 0. So when delta is 0, set it to be 1. So now h1 of k1 plus 0 times delta gives us 2. So there's a collision there, so we need to keep probing. So now compute the offset at 1 times delta. There's still a collision. Keep incrementing the x value. So now 2 times delta, which is 4, and we found a free slot. So insert that key value pair there. And the last one, k3. So from before, h1 of k3 is 2 and h2 of k3 is 10. Delta is then 10. And we have a hash collision. So 1 times delta now gives us 12, and that slot is free. And we reached the end of the new table. So get rid of the old table and replace it with a new table. And let's finish inserting our last key value pair from before, which is k7. Now suppose k of 7 is equal to 15 and h2 of k7 is 3. Then our delta value is 3, and we're able to insert it at position 15. Okay, that is double hashing in a nutshell. If you like this video, give it a thumbs up and please subscribe. And if you're confused about something, drop a comment. I'll try and get back to you. And in the next video, we're going to be looking at how to remove elements from a hash table using the open addressing scheme. Guys, thank you so much for watching. Catch you next time.